Hi there, welcome to Lesson 8. In this lesson, we will still consider some topics related to time series analysis, but from a slightly different perspective from what we have said until now. For example, we will try to combine results from time series with things that we have discussed under extreme value theory. So, for example, we will see how we can try to play with the maxima of a time series when we know that obviously the i.i.d. hypothesis that we made in modeling maxima until now does not hold. Moreover, we will drop one of the important assumptions of the models we have considered. In fact, we will consider what happens when the volatility, when the variance of our time series changes over time. That's why we will introduce Arch and Garch models in order to play with heteroscedasticity. It is no big surprise that in any serious, non-trivial time series model, the i.i.d. hypothesis that we have used in extreme value theory does not hold. So if we play with an autoregressive model, a moving average model, an ARMA model, and a Riemann model, clearly we have that we cannot assume that our observations, our x's, are i.i.d., so independently identically distributed. This means that obviously one of the fundamental assumptions for the Fisher-Tippett theorem to work, and also for the other results that we have considered, does not hold. So if our observations are not i.i.d., we have no guarantee that the Fisher-Tippett theorem works. So we have no guarantee that if we take the normalized maxima, we can get one of the three extreme value distributions, the Frechet, the Gumbel, or the Weibull. Luckily for us, there is a way out, so there is a solution to the problem. And this solution requires the imposition of the so-called D conditions. Now, if these D conditions are satisfied by our time series, then we can still get extremely useful results in terms of maxima and minima. We will see that at the end of the day, we have to introduce another parameter that we will call the extremal index, and this parameter will allow us to generalize the Fisher-Tippett theorem. So we can still play with the GEV plus this extremal index parameter that we will see will pop in our results for what concerns the normalized maxima. And luckily for us, these deconditions are not so difficult to be verified in reality in most fields of applications. Not all fields of application, but in most fields of application. And for us in risk management, this means that we can still do a lot of interesting things with our data in terms of tail results. The goal of the deconditions, D and D prime, is to avoid two main things in our data. The first is to avoid an excessive clustering of extremes. So, like in earthquakes, we know that if we have a very strong earthquake, very likely just before and after this very big earthquake, we will observe other earthquakes of important magnitude. Okay, with one of the deconditions, we want to avoid observing clusters of extremes altogether. So we will try to pick one of these extremes and ignore the others. So this is the anti-clustering condition. The other condition is a condition that tries to minimize the dependence in the data and in the memory of our time series. So we want two extremes that are relatively far apart in time to behave as independent observations. So we don't want two maxima that are separated by a sufficient amount of time units to be excessively dependent. Now, the importance of these conditions is that if these conditions are satisfied by our time series, then what we can say is that the maxima we can extract from our time series will qualitatively, let's say so, is not extremely precise, but allow me to be not extremely precise in this framework, so will allow us to say that these extremes are qualitatively equivalent to extremes that could come out from a sort of associated i.i.d copy of our time series. So it's like we have our original time series with its own dependent structure, and we create a sort of i.i.d time series, and we can build a connection between the maxima of the two time series. This is the job, if you want, heuristically speaking, of the D conditions. Now imagine that you are during a crisis, so you are looking at your portfolio. You will see very likely that several large losses will happen, several defaults will happen, and the size of the defaults is likely to be important. So what you have is that you risk to observe several extremes altogether, so they create a cluster of extreme events. Now, the condition D prime tries to avoid this, so it's a condition that tries to minimize the risk of observing a cluster of event. We will see how we can translate this from a practical point of view, but the intuition is just to avoid the fact that in a given time interval we can observe too many extremes. Condition D is the condition that we impose in order to take care of the memory of the process. So it's a condition that we use in order to avoid the fact that the time series keeps memory of past extremes, past maxima, past minima too much. So if you impose the decondition, you are essentially telling that if you take two observations and these observations are separated by a sufficient time interval, so if we take two observations that are sufficiently far apart in time, then they can be considered as independent. So they don't care about each other. So if we have a stationary time series that also satisfies the deconditions, what we can do is we can build a sort of connection between the maxima of this time series and the maxima of an associated i.i.d collection of observations whose maxima essentially are mimicking the behavior of the maxima of the time series. In reality, we will see that the maxima of this associated i.i.d collection of observations will be, once normalized, modeled using the GEV, as we know, and then starting from this GEV, imposing the so-called extremal index, we can go back to the original maxima of the time series we started from. On your screen, you can see the formal representation of condition D that we call asymptotic independence. Now, condition D is a so-called distribution mixing condition. The interpretation of condition D is quite straightforward if you have a look at the equation there. When we require the probability of the maximum for I in the union of A1 and A2 to be essentially equal to the probability of the maximum in A1 times the probability of the maximum in A2. So what we are requiring is nothing more than the fact that if we consider our time series and we take two different time intervals that do not overlap, the more our time series grows, so the more n tends to infinity, the more these maxima that we can compute from the different non-overlapping intervals become independent. And in fact, if we consider their joint behavior will correspond to the product of the marginals, okay? In other words, we are imposing a condition on the blocks of the block maxima approach that we know is one of the approaches we can use to play with maxima, minima, and whatever we want in extreme value theory. Condition D prime is the condition that takes into account the problem of clustering. So when you impose D prime, you are imposing an anti-clustering condition. If you take a time interval, you don't want to observe too many maxima in this interval. So you don't want to observe many extremes that are close together. The representation is on your screen, and more in general, if you are interested in going more into the details of the modeling of non-i.i.d sequences for what concerns extreme value theory, a wonderful book I want to suggest is the one by Falk, Hüssler, and Rice that you see on your screen at this very moment. To verify that our time series satisfies the condition is not at all a trivial task. Yet, in our applied lesson, I will try to teach you some tricks, some heuristics that you can use. One of these is, for example, the so-called record plot, which is a plot that we can build using records. Records, like in sports, are nothing more than what is the biggest maximum so far. So you are observing your data, you are looking at the maxima that you can get through the peaks over threshold or the block maxima approach, and you have a collection of maxima. Nevertheless, among these maxima, you will always have a biggest value that will be the record until it is not surpassed by another even bigger maximum. So looking at the behavior of records over time, you can find interesting characteristics about your time series. But we will see that in the applied part. Nevertheless, there are good news, and it's the fact that even if, in order to be precise, we have to verify that our time series satisfies the deconditions, in reality, most models that we can play with in our settings, so autoregressive, moving average, ARMA models, these models are implicitly satisfying the conditions if they are stationary. If our time series is stationary and satisfies the deconditions, we have the following result, which is a generalization of the Fisher-Tippett theorem. According to this important theorem, if our time series satisfies all the conditions, what we have is that the normalized maxima will still converge towards a non-degenerate distribution. But this distribution is no longer the GV that we have considered before, but it's a distribution H. And this distribution H is nevertheless a distribution that we can characterize is a GV to the power theta, where theta is the so-called extremal index. Please notice that the distribution G, the GEV, the generalized extreme value distribution, is a max stable distribution by definition, okay? And if we take the GV to the power theta, also the GV to the power theta is max stable. The quantity theta, the extremal index, is a quantity that lives in the interval 0, 1. And it's a measure of the dependence in our time series when we look at the dependence via the extremes, via the maxima. Now, this quantity that lives between 0 and 1, it is trivially 1 when our time series is made of i.i.d observations, because in that case we recover the basic Fisher-Tippett theorem, because we have that the normalized maxima will converge to a GEV to the power 1, so which is a GEV. So we are back to the standard framework. In all the other situations, when there is dependency in the data, we have that theta is smaller than 1. In principle, it can be exactly 0, but this is an extremely, if you want, pathological, degenerate case that we do not consider. So for us, theta will always be smaller than equal to 1 and strictly larger than 0. If we have a collection x1, x2, xn of i.i.d. observations with distribution f, we know that the distribution of the maximum can be expressed as f to the power of n, okay? Where, I repeat, f is the CDF of our x's. Now, if the different quantities x, x1, x2, x3, xn are not i.i.d., but there is some dependence, and this dependence can be somehow extracted by the theta index, then we can say that the CDF of the maximum can be expressed as f to the power theta n. So not only n as before, but theta n. A simple example can help us in understanding the usefulness and interpretation of the theta index when we have time-dependent data and we are interested in tail risk. So, for example, in computing quantities like the valid risk, the expected shortfall, and so on. Assume that we have to build a dike to protect ourselves from flood. So this is a very Dutch-specific example. Now, we want to build this dike with a 95% confidence for the next 100 years. Now, historical data tell us that there is a 99.9% probability that the water height will be below 10 meters, so the 99.9% quantile, or the 99.9% valid risk, if you want, in financial terms, is 10 meters. For what concerns the 99.95% case, this is 11 meters. Now, if our data are i.i.d., what we have is that the dike should be 11 meters. This is something that we can easily observe by the fact that obviously we are considering our yearly observations, and if we take 100 years and we assume the data to be i.i.d., we have that 0.95 is more or less equal to 0.9995 to the power 100. Again, I repeat, if we assume i.i.d. observations. If conversely we assume that our observations are not i.i.d. but stationary with a theta parameter of 0.5, then we see that 0.95 is more or less equal to 0.999, and this quantity can be taken to the power 50, which is exactly 0.5 theta times n 100, so 50. And we discover that in this situation, then 10-meter dike is sufficient at the 95% confidence level. There are different ways to estimate the theta index, the theta parameter, the extremal index. Together, we will just consider one of these methods, that is to say, the block method. Heuristically speaking, the block method is nothing more than a method that combines the block maxima and the peaks over threshold. Why? Because of the deconditions. In the block method, the idea is to split the time series into blocks, possibly non-overlapping blocks, like in the block maxima approach, and then we will just pick the observations within the different blocks that will lie above a given threshold. Okay, so differently from the blocks maxima in the basic setting, in which we pick the maximum of every block, here we also impose a threshold, and we will only pick those observations that are above the threshold. And it may happen that within the same block we have one or more observations that lie above the threshold. Again, here you can imagine that the problem is to decide the size of the block and the level of the threshold. But assuming that for the moment this is not a problem, this is what we will do in the block method approach. Assuming we find a good compromise in the trade-off between the number small k of blocks in which we split our time series and the size r of each block, then we can easily compute the theta index using an apparently trivial quantity. Only apparently, because the derivation is not at all trivial, but in any case, from a practical point of view, an apparently simple quantity, which is the quantity capital K over n, where n is the total number of exceedances in our time series, and where capital K is what? It represents the number of blocks with at least one exceedance. Okay, so small k is the total number of blocks, capital K is the number of blocks with at least one exceedance over the high threshold that we have to find. Small n is the total number of observations that we are considering in our time series, and capital N is the number of exceedances over the high threshold. It goes without saying that the big problem is to identify the numbers r and small k, which is not at all a trivial task. Also there are some heuristics that we can try to use. But again, as many results, not only in extreme value theory, but in statistics in general, as I told you in the first lesson, you learn by doing. You learn by trial and error. That's why I like to say that statistics is a science, because it's a very strong science with many fields of application, but is also an art, because you have to learn. And the best way to learn is to essentially practice. In the practical part of our lesson, later on, we will see how we can play with the extremal index in R, for example, using the x-index function.